All right, so as I was saying, as we know that differential pressure transmitters, they can be used to measure flow rate, and they can also be used to measure level through the hydrostatic pressure. So we know that hydrostatic pressure is the density of the fluid times the gravity times the level. Okay, so when we talk about level, so times the height, right? So when we talk about height, the height that is in this equation is the level. Okay, so if I have the pressure of my tank divided by the density of the fluid divided by the gravity, then I will have the height of the fluid that is in my tank. But today, we're gonna leave this for another live. So today, I'll be talking just about measuring the flow rate with a differential pressure transmitter. Okay. So what we have here the Fluke 789 process meter. We have here the Yokogawa DP sharp transmitter, and also we have here the Trax device communicator. Okay, so expensive piece of equipment. For those of you who are related to instrumentation and automation, or even are currently working in the oil and gas industry, you know how these piece of equipment are expensive, but EDACO managed to purchase them to provide good quality and courses to our students. All right. Okay. Let's go to what brings us here today. So what we have here, we have a centrifugal pump. Oh. So there had just been a drop in pressure, so the pump has started. It's not what we intended, but okay, it stopped. Okay, so we have here, what we have here? We have here a centrifugal pump. We have here a pressure indicator. We have here a hydrometer. And then we also have here a rotameter. Okay, so these are the equipment that we're going to use to aid us in measuring our flow. Okay, so what we're going to do now, we're going to start up the pump, right? So when we start up the pump, you guys are going to see that the percentage of my flow will change, okay? Because right now we are reading minus 1.4% of our differential pressure, okay? So here, if you look at my tracks, so we have our lower range value is 0 millibars, and then our upper range value is 800 millibars, or 800 millibars, okay? So if the flow is 0, okay, there's an airplane passing by, it's gone. Okay, sorry for that, for the interruption and the noise. So as I was saying, if you look at our tracks, so we have our lower range value is 8 millibars, 0 millibars, okay? And our upper range value is 800 millibars, or 800 millibars, okay? 800 millibars, that's what I wanted to say. All right, so right now the pump is shut off, it's shut down, right? The pump is off, so no flow, no pressure, right? No flow, no pressure. So this is what we are reading currently. And our transmitter is sending a 3.771 milliamps, right? Meaning is way below of our zero set value, okay? So we have calibrated our transmitter, and the meaning of this is that when we reach 800 millibars, the transmitter has to send us 20 milliamps, okay? So when we reach 50%, the transmitter needs to send us 12 milliamps. So this is what we call the 5-point calibration, okay? So I'm gonna start up the pump. I'm just gonna open the valve, right? Because what we have here, we have a pressure switch, we have here pressure switch, which controls our pump. Since I closed this hand valve, what happened is there was an increase in pressure, right? So the pressure increased to 3 bars, which is our set point to shut off the pump, right? So right now the pump is off because there is pressure. So if I just open this valve slowly, because I need to do it slowly, so I cannot have a sudden increase in pressure in my system. So I'm gonna do it slowly. So when I open this valve, what's gonna happen is that the pump is gonna stop because we're gonna have a drop in pressure, right? Okay, let's go. Let's go. And then when the pump starts, I will have flow through my pipeline, okay? And as soon as I have flow through my pipeline, right, my flow percentage, my pressure percentage will start to increase, and the signal as well, all right? Because, okay, right now what we have, the differential pressure that we have here is 11.9%, now 11.8%, okay? So my transmitter is sending 5.8 milliamps, okay? If you can look here, you can see it, and the pressure is 93.04, well, let's say 93.6 millibars, okay? So right now we are just reading 11.9% of the pressure that is in our Venturi tube, because what we have here, we have here a Venturi tube, right? So we have here, this is a Venturi tube. If you can look here, so we have the bigger diameter, and then there is a small diameter. So what's happening is that we have a sudden drop in pressure, because these are head losses. We have a sudden drop in pressure between this bigger diameter and this smaller diameter, right? And what we have here our manifold. So we connected our low side to our low diameter, and then we connect our small diameter, and then we connected the high side of our transmitter to the bigger diameter side, because this is our inlet, okay? This is our inlet. So we have, this is what the continuity equation says. When we have a sudden change in pipe diameter, so the flow will stay the same, but the pressure, there will be a sudden drop in pressure. So we will have a higher pressure on this side, but a lower velocity. And we will have a lower pressure on the smaller side of the pipe and a higher velocity. So by measuring the difference in pressure between the two sides, we can get our flow rate through the system. So this is what we are doing. So I'm just going to increase the flow, okay? I'm just going to increase the flow in the system, and then what you're going to see that the percentage is going to come up, going to increase, okay? And of course, the signal of our transmitter is going to increase as well, and of course the pressure, okay? So what we're going to do now, so now we are reading, let's try to put it at 50%, okay? So we are roughly almost at 50%, right? At 50%, and our pressure is now 360 millibars, and the signal is 11.18. So we are roughly at 50%, so, or at 40%, right? At 40%. So now our added tank, we need to decrease the level of our tank. So if I close the valve, which means I'm shutting the system down, this means that I'm closing the flow. So the pump will shut down, and then we will have no flow, which means that our transmitter will be giving us a negative percentage because there is no flow. So we need to set up so there is no flow, which means the transmitter will be sending us the 4 milliamps. Okay, 4 milliamps, because there is no flow in the system, right? So now the question is, how do we get the flow rate through these numbers? Okay, what are these numbers telling us? Okay, can you share your ideas? Can you tell us? Are you able to tell us what are these numbers? What these numbers mean? Okay, what are these numbers telling us in terms of flow rate? Okay, so we're gonna compute this to our PLC system, and then to our HMI and SCADA system. So what we're gonna have is the square root extraction as well in there, the process, so that it can compute the signal versus the flow rate that we have in our system compared to the pressure, differential pressure that we have as well. So right now there is no pressure because the pump is shut off, right? So this and some other instrumentation and automation technologies and knowledge are being shared through our Facebook page and LinkedIn as well. So please follow us. Just go to LinkedIn or go to the Facebook page and then look for EDACO, EDACO, and you'll be able to find us. Follow us and try to get more insight and in regards to automation and instrumentation processes. Thank you very much. This is what I wanted to share with you guys. Continue to follow us and be safe. Thank you.